Actually, to be honest, I'm to the point today that I'm ready for it to be over with. It's been one of those days that pretty much anything I could do to make the day go wrong, it's gone wrong. I got here this morning, everything was fine. Went for my lab, the lab you'll be doing later. All the drivers were deleted from the computer, so we had to reinstall the drivers for the development boards all over again. And then I didn't have the right part number, so it took a while. Got the lab to work right, but when we went to program the boards, we had a problem. Okay, as I recall, let me just kind of hit the highlights here, and I'm just using these slides as kind of a guide. I just want to make sure that I have hit the highlights here of that there. Where we talked last time is that we talked about numbering systems. Number systems. And we talked about how base 10 works. And base 10 works when the number 2, 3, 6. This is 2 times 10 squared. This is 3 times 10 to the first power, and this is 6 times 10 to the 0 power, right? That's how any numbering system works. So if I want to convert from any other numbering system, I can follow the same that there. So if I threw a number at you, 7, 8, well, let's not use 8. Let's use 775 base 8 right there. So this is an arbitrary numbering system. And I reserve the right on the final exam to ask an arbitrary numbering system. And I was asked when I did the exam this time, did you teach base 6? And I go, no, I did not. But I taught how to change from one numbering system to another. So you need to realize that there. So when we look at this number, it's 7 times 8 squared plus 7 times 8 to the 1, which is 8, right there, and 5 times 1. So this answer would be, take it out of programmer mode, put it in standard mode or scientific mode. So 8 squared, right there, it's 7 times 8 squared, so 7 times 8 squared equals plus 7 times 8 equals 504. Is that right? That there? Plus 5. So it looks like 509 is the right answer to that. So that's how you would do that. Now, I will not ask you how to go from base 10 to a random numbering system. I think all that is required is that you, at least to understand numbering, that I know that you understand how a numbering system works, that if you could go from a random base back to base 10, you have enough of a basis for that. So with that said, we spent a lot of time talking about base 2. Base 2 is the typical numbering system we use in digital. And we have two symbols, 0 and 1. And so the number 1101, 1001, base 2 is going to be, and I'm just going to write these down. We've got our 1s, our 2s, our 4s, our 8s, our 16s, our 32s, in our 64-bit columns right there. And we just write, and you could do it however you want. I just simply go through, in this particular case, I can mark through the ones that are zeros and just add the rest of them up right there. That's one easy way of doing it. So we've got a 1 here, so we can circle that one. We got a 1 here, we circle that one. We don't have this one. We have this one. We have this one. Am I missing one? 1, 2, 3, 4, 5, 6, 7. I'm missing one there. Am I not? Oh, 128. I didn't go far enough. right there. Start this over again. 1, 2, 4, 8, 16, 32, 64, 128. An 8-bit number goes up to 255. If I add all those up, I get 255. So if I just start at this here and move left, I can circle this one, mark through this one, mark through this one, circle this one, mark through this one, and just add those numbers up right there. If I add those numbers up, right there, I can just very simple here. It's going to be 1 plus, it's probably easier to do that there, plus 16 plus 64 plus 128 equals 217. If I use the calculator to do the same thing, right there, and if I said 217, if I put 217 in there, binary is going to be 1101, 1001, which is the same thing. So going from base 2 to base 10 is fairly easy. You could do it pretty much this way. Going the other way is a little bit more difficult, but going the other way is really fairly straightforward. And expect to see some questions on the final exam on converting there. You can use a calculator for checking, because most people who teach this class say no calculators allowed. But what I want to see is work. You'll see the comments show your work, which means I expect to see something like this shown on the exam paper. That's there. If I want to convert a number to, and again, I know I'm going quickly because I've covered this before, but I think it's important enough to cover it a second time before we get into the new material. If I want to convert a number such as 176 to base 2, I do the same thing. I'm going to just write down 1, 2, 4, 8, 16, 32, 64, 128. Right there. And I'm just going to subtract the largest number each time. Will 128 go into 176? Yes. Right there. So I write 128 and I subtract that there. That's going to be a 6 carry. That's going to give me an 8 here. That's going to leave me with 48 left there, right? I put a 1 here. Can I subtract 64? No. So I put a 0 there. Can I subtract 32? Minus 32. So I'm left with 16 there, right? So 1, and then I can just go ahead and put the rest zeros here, because if I subtract the 16, I'm left with zeros right there. So the answer is 1, 0, 1, 1, 0, 0, 0, 0 right there. Is that the right answer? We started off with, what did I say? 176. Oh, we need to clear. 176 is 110110000. That's it. So we get the right answer. So converting from base 2 to base 10 and base 10 to base 2 is not a difficult process right there. However, you still have to do work. And there's a rule of thumb is that, I can't remember what it was said, I think it was Bill Gates that might have said it, is that I hire the laziest engineers I could hire because they figure out how to get the most production out of the least amount of time. So in order to avoid doing this, we use a numbering system that we don't have to translate. That's there. And what we use is base 16. And the reason we use base 16, and again, that there, is because if I go from 0, 0, 0 to 1, 1, 1, 1, and I convert those, this is 0 to the number 15 right there. We have 16 symbols there, 0 to 15 right there. So I can write a table that is going to show between 0 and 15 the exact translation, and there is no math to translate between them right there. So if I generate this table, right there, and I'm going to generate it here. If you let me cheat here, and it's not really cheating, I'm just putting the ruler up there so that my handwriting improves. And I write the numbers 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 1, 1, 0, 0, 0, 1, 0, 0, 1, 1, 0, 1, 0. And I know it's annoying listening to do this, but if I don't do it, for some reason I've gotten the habit of saying this as I do it, I mess up. 1, 1, 0, 1, 1, 1, 1, 0, 1, 1, 1, 1. So if we look at this right here, and I go through here, this is decimal 1, 0. This is decimal 1, 2, 3, 4, 5, 6, 7, 8, 9, and then we're going to write the letter A for 10, B, C, D, E, and F right there. So now if I see a binary number, 1101, 1101, 1100, 0100, I just look at the table and I say that this is D, D, C, 4 right there. I just look at the table and can translate, can do it right there. Same thing, if I write the number C14E, I can say in binary that's going to be 1100, 0001, 0100, 1110. I can do that without doing any math. Now, there's no cheating. It's not cheating on the final exam for you to write this table. It's cheating if you bring the table in. But writing the table down before you answer the questions is perfectly allowed and probably encouraged. That's there. Matter of fact, I've been known to confuse C and D on a regular basis. My dyslexia will kick in there. I don't know if you know the term dyslexia, but you transpose letters when you write there. So me and C and D sometimes will confuse those two. That they're 1100 is C, 1101 is D, but sometimes I get those two backwards. I don't know why. It's one of those things that happen when your brain short circuits. And you don't get to 50 plus years old and not have a few short circuits. That's there. Most of you are 20 something and you probably short circuit once in a while, right? Admit to it. There's some short circuits you run into. That's it. So that's really the numbering systems we're going to be working with, is hex and decimal and binary. That's there. Those are the three numbering systems we're going to be working with. That's there. So you should be able to go back and forth between the three of them. In microprocessors and microcontrollers, we probably use hex 90% of the time. That's there. There. Now we have to translate between hexadecimal and decimal from time to time. That's there. So now, in addition to numbering systems, we have what's called a series of codes. And a code is simply a way of representing information in numeric form, right there. So you'll hear, codes have been around since man has been fighting wars because people like to send encrypted messages using codes. But we're not using codes here to encrypt messages. We're just figuring out a way to store data in a fashion. And one of the simplest codes, well, I wouldn't say simplest codes, one of the most common codes, and I need to slow down. I think I'm talking fast today. I came in late and I'm talking fast. No one's stopped me on it, probably because I'm repeating that there, but I think I'm talking a little fast. One of the most common codes we run into is something called the ASCII code, right there. And the ASCII code is all the letters of the alphabet, and I'm not even sure if I spelled ASCII right there. There. But the ASCII code is a way of representing all the characters in the English/European languages there between the numbers of 0 and 127. It's a 7-bit code. right there. And I don't know if I've got internet in this room or not. Nope. Maybe if I do this here, network settings, doesn't see any networks. It sees no networks in this room. That there. Okay, that's fine. If I go back to the book here, we'll find the ASCII code here. Yeah, here it is. Right there. And right there. I'm going to shut down all these books. Let's go one page. Right there. And I did miss out, there's two I's there, ASCII. That there. It's abbreviation for the American Standard for Information Exchange. I knew it didn't look familiar. I knew the ASC was right. I forgot to put that there. So, right there. And that there you can see that it's pronounced ASCII right there. It's a 7-bit code right there. And here's the table for it. I don't know if I can rotate this right. Yeah, rotate this right here and rotate it again. And rotate it once more. Right here. So when we look at our ASCII code, this is the standard ASCII, and it goes between 0 and 127. Can we see that, or do I need to let me turn off this front light? I think as I recall, yeah. I don't know, all the lights, every light switch I come in this building are backwards. The front light is toward the back of the room, and the back light is toward the front of the room. So, but as we look at this table here, you will see all the characters actually starting with 32 right there. Before the character 32, the first, and these are decimals, from 00 to 1F or 0 to 31, those are all control characters. Now, the most common of those might be line feed or vertical tab or form feed or carriage return. Null is simply, there's no character. Null is used to represent the end of a string right there. So you see all these various end of transmission. These are various control characters right here. So we start out with the space, then we get up with some punctuation number right here. And you can see exclamation mark, quote, that there. And these are all special that they're starting at location 48 is the number 0. And that goes to number 9 goes to 57. Then we go into more punctuation. And then we get to our alphabet, A through Z starts at 65. The capitals are not the same as the lowercase right there. You notice that they're 32 apart from each other. So this is 41, and this is 61S. That there. They're all in order right there. And it ends with the delete key being number 7F right there. That's the standard ASCII character set right there. Right there. There's something else called extended ASCII that goes up to 255, and that will include things like the top half of the integral sign, lower half of the integral sign. I don't believe it contains a lot of the Roman alphabet, or not Roman, a lot of the Greek alphabet, things like theta, omega, a lot of those are in the extended character set. As far as I know, none of the Arabic characters are in the extended character set. That there. There is no equivalent in the ASCII set of that there, which has been kind of a problem with transmitting Arabic text via the internet. That there. Recently, now most of it's done using pictures instead of trying to do it from the ASCII characters. That there. So, matter of fact, if you kind of a side note that there is that if you listen to a lot of the historians in the rise and fall of the Arabic civilizations, one of the reasons that they said that the Arab civilization started to collapse was when English when you look at the European languages, they were much easier to use the printing press for. So in the late 1400s, the printing press came out, which was designed to be used for language such as Italian, French, German, where Arabic was not quite as easily translated to a printing press. So Arabic had to be translated by hand, printed by hand, where text can be used with a printing press and teletypes and things like that. So that's been one of the problems when we look at there. And a number of historians have pointed to that as one of the leading reasons why, when you look at Arab culture, it was the driving force of civilization for 500 years, 800 years probably. But when the printing press came out and the languages from Europe can be easily printed into book form and newspaper forms, the information age came around in Europe, and that did not move into the Arab world very well. Now, of course, it does because there are other methods other than the printing press. Matter of fact, the printing press is hardly used at all. I mean, there are places where it's used, but now it's usually laser printers or some type of other printing. Books are still using typeset, and newspapers still use some form of typeset, but most data transmission today, where do you read your news? Pick on you. Where do you read your news? Hopefully you read a newspaper. Is it on your phone? Hopefully, don't tell me you get your news from Facebook. Facebook's not a good place to get news from. I get my news, to be honest with everyone, is I read, right there is where I get my news, and I read it, this is one of the English newspapers, right there, and I read my news on this here. I pop the keyboard out and I sit in my recliner and I read my news here. I don't read a newspaper because I don't want stacks of newspapers back up there. So the newspaper is being replaced by digital there. However, still, we want to store documents. When you write lab reports, what do you use? What do you use to write a lab report? What? You use a computer, right? Hopefully you're not writing. You use Word, right? Microsoft Word. Well, again, that is stored in ASCII form in a document someplace. Now that's there. So if you write a program, it's going to be stored in a text file. That's all stored in ASCII form. Now Word will store the document in ASCII form, but have a whole bunch of other control type information with it, or if you put images in there. But the text is all going to be stored in ASCII. One character there. In a general rule, when you look at a text document, it's one character per letter, and one page roughly is 1,000 characters. There. We used to use a rule of thumb that a 30-page document would be about 30K in text form. If it's in Word, it's usually a little bit more because of all the formatting information. So getting back to my discussion, there is, and let me correct my here and put the second I in there. I knew it didn't look right. There. So, but we look at this, and this is used for text right there. So the ASCII code is the most common. Now you cannot add, subtract, multiply, and divide with ASCII. It's a code. Codes you cannot do math operations on. If I have the character string 32 and multiply it by the character string 45, I get garbage. So I have to translate this to the number 32. Now if you're working in C and you do a scanf and you tell it that you're going to read an integer, it does the translation for you. But if you read it as a string of characters, it's going to store it in a string. So when you work in C, you have a %s type. Anybody remember %s? You had a %c type, right? You remember that there? And you could declare a variable as char, which is 8 up there, and we could say F name right there, and 25, for example, like that. Anybody remember something looks like that? Let me write a little clearer. Char, F name, bracket 25. What does that represent? That's setting a variable up called F name right there. That's a place in memory right there. It points to a place in memory. It's 25 spaces right there. Right there. They're each 8 bits wide right there. And each one of these is going to contain a single letter. And I'm not going to go ahead and spell out the whole thing. That's a K. That there. So I can store a string of letters up to 4 letters, because the last letter is going to be a 0. I'm going to show it as a 0. That's my null character. And that's how strings are stored in computers. We store them as an array of characters. Some people, when they program, they will declare this as a string. Right there. So some versions of C support the string type, some do not. From what I've been hearing, most people here say they have not seen the %S sign, so they have not seen the string type. You've only seen the array of characters. And that's standard ANSI is a string of characters right there. So that's what you see in computer programming. And we can see that when we write software for microprocessors. We can send a string of characters to a LCD display. We can send it to a stringing banner. So we could do all kinds of things up there. So when we look at digital, we will use ASCII from time to time. We won't use it in this class. We won't get to that point up there. So, but that is a code. ASCII is a code. It's not a numbering system. Another one you will see, and we will see in this class, it's called BCD. This is binary coded decimal. Now, binary coded decimal is basically the zeros is the table and this table here, and we chop it off at 9 right there. So when we look at binary code decimal, it's the numbers 0 through 9 written in binary form, and I'm not going to go through and do the whole thing here. 1 0 0 1 0 1 9 right there. Now, we use binary coded decimal typically when we input and output from a digital system. You're driving a car, let's say you've got, I'm going to have to pick on a car other than the 2 Malaysian brand cars because they have analog. We can pick on the odometer, okay? You've got an odometer on your car. And my car is relatively new, and it's got 007-215, for example. So I've got 7,215 kilometers on my vehicle, right? Now, inside the computer in that car, what did I say? 7215, right? 1C2F. 1C2F. What if I didn't convert that to binary code decimal and I displayed 1C2F? What's that mean to me? Well, I'm a software geek. It means something to me. It tells me it's a hexadecimal number and I would convert it to decimal. But what would that mean to your sister or your brother or your dad, unless he's a computer programmer? Nothing, right? So we would convert that to binary coded decimal. So there are software algorithms to do that there, but we cannot do math on BCD. So when we read in decimal type information into our computer system, and I'm jumping ahead to computer systems because decimal, this is digital, and you're going to be leading into computers. It's going to be BCD data we're going to read in, and it's then going to be it's going to be automatically converted to binary. And we're going to manipulate it. We're going to do all kinds of stuff. But before we output it, we need to convert it back to BCD. Now, if you're dealing with a computer system in a computer language, that's fairly straightforward. You can do a scanf right there and give it a %I right there, and that's going to right there, and we're going to say A. We do a scanf and we read the number A, and it's stored as an integer there. So the compiler does all that for you. You can do a printf right there, A %I right there, and that tells the compiler that A is an integer, and we're going to send it to the printer, and it's going to send it out as a decimal number right there. It's not going to spit out binary information unless you give it a %X. You can tell it to spit it out as a hexadecimal number if you want, or binary if you want. You have that option. I'm sure you probably didn't do that. So with the scanf and the printf, if you're dealing with a computer system, takes care of that BCD to decimal or to binary and binary to BCD conversion for you. There. Unfortunately, if we're dealing with hardware situations, you're reading a keypad. You're not using a scanf. There. You're going to get the number 6, and you're going to store that. You're going to get the second digit, a number 5. You're going to store that. You're going to get the third digit, number 6, and you're going to store that. And then when you hit the enter key, then you've got to do the conversion into binary yourself. There. So when you deal with embedded systems, you have to do the conversion yourself. Same thing if you're outputting the information to a LCD display or a numeric key display of some type, you need to do the conversion yourself. And we're electrical engineers. My experience has been more electronics. In the U.S., they don't separate electrical engineering and electronics engineering. They're the same degree. And so electrical engineers take many courses in electronics, and people who do electronics take courses in electrical. So we don't have separate programs. And just kill a few minutes here and kind of go off on tangent. The reason for that is fairly simple, is none of you know, you may think you know, but none of you know what you're going to do for a living 10 years from now, right? You hope to be working someplace as an electrical engineer, I assume. I mean, if your goal in life is to open up a motorcycle shop and sell modified hot rod motorcycles, you probably should get a degree in mechanical engineering and not electrical engineering. If your goal in life is to open up a food stall and sell roti canai, you probably ought to, go to someplace that find somebody who does a great job of running a food stall and sells roti canai and learn how to make roti canai, right? So if you're sitting in this classroom in this degree program, I have to assume at some point you want to work as an engineer. If you don't want to work as an engineer, you probably should do something different. Now, I understand I'm in Malaysia and some of you don't have the same choices as Western countries, and some of you are kind of funneled into engineering programs because there's a national need for engineers and they feel that they need that there. Whether you wanted to become an electrical engineer but you were funneled into this, you have to accept the fact that you're being trained as an engineer, and it's probably what you want to use at least for the initial part of your career. We were talking yesterday at lunch, and most engineers probably find themselves after about 10 years moving into management positions within companies. That's there. And that's something you need to keep in mind, because if you're going to become a manager, that's a different skill set than engineers. And I'm completely off the topic. Don't take notes. It's not going to be on any final exam or any quiz. But management requires soft skills. When I talk about soft skills, I'm talking about things like doing what I'm doing right now. Getting in front of a group of people. Hopefully most of them are awake and paying attention. Sometimes they're playing with their phones. Sometimes they're dozing off. And trust me, I see everybody in the room, and I can see people dozing off. Nobody's dozing off here, but this morning in my 8 o'clock class, by all means, there's people dozing off. That's there. But regardless, you need to be able to speak in public. Now, Malay is your first language. Most of you are not comfortable coming up here and speaking in English. I understand that. If you told me I had to speak in Malay and teach in Malay, I probably wouldn't have taken this job. I can speak a little bit of Malay. I can get myself a bus, a truck. I can order food. Funny story was, I'll tell that later, is that I can hear Malay and I can understand a lot of it. For me to lecture on technical material in Malay, forget it. It's not going to happen. That's there. Because it will take me so long to translate in my mind, even if I spoke Malay and knew it better, it's not going to happen. Unfortunately, engineering is surrounded with English textbooks, English tech manuals. All the computer programming languages are based on English words and syntax. So the engineering field is unlike many other fields. If you're going to be studying Islam, for example, and become you would probably want to make Arabic your primary second language, correct? The Quran is written in Arabic. A lot of the early books are written in Arabic. Just the same thing in the U.S., for example, or in Europe. If you want to become a Christian minister, they're forced to study Greek and several other languages. A lot of the early translations of the Bible were in Greek and Aramaic. That's there. So, and even Hebrew to a large degree. So if your goal is to study Christian theology, for example, you would have to learn the languages that those are written in. If you're going to be studying Islam, you would study Arabic. That's there. Fortunately, the Islamic religion only has one language that everything's in, Arabic. That's there. So, the Christian and Jewish religions have gone through, since they don't have the original books, and they've been translated into various other languages over the centuries. Some of the early texts are in Hebrew, Old Hebrew. That's the Old Testament you will find there. A lot of the books from the time of Jesus are in Aramaic. That's the language he spoke at the time, which is the version of Hebrew. And then a lot of them were later translated into Greek. And then a number of them were then translated into Latin. So you end up with 4 or 5 languages. That's why when you read a Christian document, it's very hard to determine what the original is because it may have been translated 4 or 5 times. That's there. And and this is not a section of the course where I'm comparing religions, but that is an issue that the Christian religion has, is that the original text is fairly well lost because of multiple translations with multiple translators over the years. That's there. Where when you look at, say, in the Islamic religion, you have one original text. That's there. You can argue whether or not an English translation is correct or not. But you're probably going to find that the English translation is probably more correct because the original Arabic that was written from is still available to compare it to. That's there. So if you have 4 English translations, and there's like 7 different English translations of the Quran. I don't read Arabic, so if you think I don't know any Malay, I don't know Malay. I know a little bit of Malay. I know absolutely no Arabic. 4 languages is my weakest link up there. But I can read all 7 English translations And they're going to be fairly close to each other. The reason is that all 7 translations went back to the original Arabic text. Correct? Where the 7 translations of the Christian Bible went to different translations. And quite often, a lot of the translations of the Christian Bible are rewritings of the King James Version of the Bible. So they go back to an earlier English translation. They don't go back to the original text. That's there. So when you look at, the reason I went into this whole discussion is when we look at engineering, and we look at engineering documents, what is the original language you're going to find most of them in? English. And that's why I consider that a very strong soft skill for engineering managers, because chances are you're going to be referring back to user's guides, data sheets, catalogs, all written in what language? That's there. So the international language of engineering is English. That's there. The French get upset when you tell them that because they think that the French should be the dominant language. At one time it was the international language of diplomacy. Since then French has become a minor language. That's there. So other languages such as Latin are considered dead languages. Nobody uses them to speak anymore. The only place you see Latin is in the Catholic Church. And there are still some, and don't ask me why, nobody understands Latin. But if you go to some Catholic churches, the Mass is given in Latin. So you've got 200 people sitting there in the church listening to a sermon that they don't understand what's being said. That's it. So, okay. Other soft skills required. Writing skills. And in your case, writing skills in both Malay and English. That's it. Because if you're writing, say, for example, as an engineering manager, operator's guides on how to run a particular piece of equipment, chances are the person that's running the equipment is going to be Malaysian. That's there. And more times than not, Malays are the dominant race. That they're probably going to be Malay. That's there. But regardless, Malay is going to be the language on the factory floor. That's there. So you need the writing skills. You also need budgeting skills. You need to how to handle money. When I say budgeting skills, that means looking at the fact that I've got a department to run and I've got $1.5 million, that there. And with my $1.5 million, I have to pay so many salaries, I have to buy so much equipment, I have to pay so much rent, that there. And you have to be able to manage that budget. That there. I spent 5 years as a department chair, and my budget was roughly about $1.5 to $2 million per year. Out of that, I had to run an academic department. So I had to put so much money into salaries, know how many people I could hire. That there, every time I hired somebody, I knew what their salary, what I could afford to pay them. Every time I had to buy a piece of equipment that broke down, I had to make sure I had money. I had to set aside. So that's a skill that a manager needs to have. Those are things that are going to progress your career. Now, personal finance is another issue, and we won't talk about that today. But that there are other skills, you need the skills to manage people. That's the most difficult. Some people are easy to manage. You tell them what their job is, they'll do their job, they don't give you complaints, they don't give you headaches, they will do an excellent job for you, no problems. They have a problem, they will come to you and they'll suggest solutions for you because they know their job better than you do. That there. Some people are a complete pain in the rear end. I've managed both. That's there. So and sometimes as a manager you have to make decisions, and that seems to be a problem that I've run into a lot. In the year or so that I've lived in Malaysia, because sometimes decision making is a very risky thing. I'm very good at making decisions. Sometimes I make stupid decisions too quickly, but sometimes you just have to make a decision, right or wrong. And you got to be willing to take chances and make decisions. Some decisions are very difficult, even if you know they're the right ones. I've been in the position of having to fire an individual, more than once. I hate to say that I've had to fire people. That you're working for me, you're a nice guy, I like you, great, we can go out, have a cup of coffee together, take Tarek, eat roti canai, talk about things. But on the job, you're a total waste of space. I got to make you go away. I can't have you in my plan anymore. You make mistakes. You produce scrap, and I'm not picking on the individual. I don't know what type of individual he is, so don't take it personal. But I'm just using it as an example. So I have to make the tough decision to let you go. And how do I do that? And still maintain your dignity and not make you feel terrible, but just simply say that this job is not suited for you. So, all right, enough with that kind of up there. You'll have lots of opportunities as you go through your career to develop those skills. But the reason I got into this is I said, in 10 years, you don't know what you're going to be doing. Many of you are going to move into management skills out there. The number one thing that is going to make you more money than anything else is not your technical skills. You could be the best engineer on the planet, and you will not make a lot of money because you do not have the management skills and the people skills and the entrepreneurial type skills. Case in point, I'll talk about two individuals here real quick. Steve Jobs and Steve Wozniak. I can't even pronounce his name. Nice big Polish name. His buddy Steve, out there. They were two buddies. They went to high school together. They both lived in in the San Francisco Valley area. Out there. Steve Jobs, not a very good engineer. Not a very good programmer. The Woz was a much better engineer, much better programmer. Out there. Everyone in the community just calls him the Woz. He designed the first Apple II by himself. His buddy Steve kind of egged him on, but Steve Jobs found the money and had the idea, but he couldn't implement any of them. He wasn't a good engineer. He didn't have the strong technical skills that his buddy Steve had, but he knew how to use his buddy Steve to start the company and make money. And then Woz said, this is no fun, this is too much work running this company. He goes off, takes his millions of dollars, and goes off and plays and has a good time. And Woz is still around. He's still having a good time. Out there, and he's a great guy. I've met him once personally. He's a really fun guy. Likes to joke. Out there, but he's not a businessman. He's not a manager. He's the typical computer geek. Doesn't want to be bothered with managing things. He wants to just give me a bunch of ICs and a soldering iron and let me have fun. Let me see what I can come up with. Type person. That's there. Jobs looks at it and says, how can I make money from it? That's there. So who became one of the richest men around? That there. Same thing with Bill Gates. Bill Gates is a very competent engineer, by this computer programmer. He's not an engineer, very competent, but he's not the greatest. But he knew how to run businesses. He knew how to manage people. He knew how to make deals. That there. So when you look at companies like that, you find that the people that are the greatest engineers are not necessarily the greatest managers. And it's the managers that end up moving up the chain. So, all right. Now let's move on to our next subject area. There. I'm not going to talk any more about codes or numbering systems. Let me pull my book back up here. Hopefully I didn't close it. Okay. Right there. Except for now I rotated it 3 times. Oh, okay. I guess that's right. Okay. As we go on to our next object right there, we talk a little bit about parity. I'm going to come back to parity. Parity is used for error detection. I think I mentioned it before, but parity simply means that you keep an odd number of ones or an even number of ones. You add a 9th bit, and that's the reason the ASCII set had 127. They used a parity bit in order to ensure that you had valid data. So right here we're looking at even parity means that as you look at this right here, let's grab it here. This is odd parity. You notice that we added a 1 here to make sure there's 3 ones. Here we got even parity. There's 2 1s, So our parity bit is a 0. Here we've got 3 ones. We add another 1 to make sure it's even. Here we got 3 ones, and this one's 0 in order to keep it odd. So you can have even or odd parity right there. And those are used typically when transmitting data from point A to point B. They're not used as much as they used to. Back in the old days of telephone modems, they were very, very important at checking errors, because you could check each and every byte as it came down the pipeline. Now they use something called a checksum that adds up all the ones and does a comparison and does by a block. That's there, because you don't want to take the time to check each and every byte. And the technology has gotten more error-free. Back when I first started using computer modems, they had these old 300 baud modems, which if you think that dial-up internet is slow, you've never seen a 300 baud modem. You hit a character on the keyboard, and 5 seconds later it pops up on your screen. Using a 300 baud modem is very, very slow and full of noise, because a lot of times that key has to go to the other end 2 or 3 times in order to get it right. Not there. So you mentioned parity right there, and I'm not going to spend any time on that much time on parity at their codes. I want to jump to the next chapter here, and as we go through and talk about logic gates. And I believe I started the subject last time. I went back and repeated some of this up there, and I know that most instructors don't like to repeat. I believe that if it's important, I need to tell you at least twice, sometimes 3 times. That's there, and not necessarily the same way each time. That's there. You know, a side note of that is that I'm trying to get a motorcycle license. That there, I bought a little scooter, and I had to take the motorcycle class last Saturday, and it was in Malay. Fortunately, that instructor said everything 3 times. So since he was giving it to it in Malay, I could understand what he was saying, because he said it 3 or 4 times different ways, so I was able to keep up with it. And the other thing is it's an hour and a half worth of material in a 6-hour class. That's there. So, all right, when we look at our gates, there's 4 basic gates that they introduce here, and I'm going to go through them again real quick here, along with their truth tables right there. So let's just kind of go through the 4 basic gates right there. The first one is the inverter. Its truth table is, and I'm going to use A, B, C for the inputs. The truth table here is, if I got a 1, 0 in, I get a 1 out. A 1 in gets me a 0 out. It just simply inverts the information. Now, every now and then you will see something that looks like this. This is a buffer. That truth table is simple A, X, 0, 0, 1, 1. It doesn't change the information. We sometimes use this for 2 reasons. One is we want to drive 4 or 5 different gates with this here. So we use this as a current amplifier to increase current. That's there. So in other words, we can only have 1 milliamp here, and we need to draw out of this, say, 3 milliamps. So we put buffers in there. Another place we will use this is that some of my signals go through here and some don't, and sometimes I'll put the buffer in between in order to ensure that they hit the same time. Between here and here, there's a time delay. I'm going to put a P in there. It's called the propagation delay. Whenever you have an input signal to a gate, the output signal occurs at a later point in time. It's not a very long point in time. It's like 5, 10 milliseconds, or nanoseconds, excuse me. I'm off by 2 factors of 1,000. Right there. But you're talking typically nanoseconds or microseconds at the most as we go through these various gates. But if we've got signals that go through an uneven number of gates, in other words, I got 2 signals here going into this OR gate, for example, here, and this one doesn't go through that there, goes straight, this signal is going to get there after this one. And quite often, instead of getting this, I get something looks like that right there. You know, there, you know, I get these little glitches that show up right there. They call them glitches, and the reason is because things are not hitting our gates at the same time. Right there. Later on, we'll look at how we get rid of that. So that's the inverter. The next one is the AND gate, and I don't know if these are in the same order. Now we can have more than one input for the two inputs for the AND gate. I'm going to show a two-input AND gate: A, B, X, 0, 0, 0, 1, 1, 0, 1, 1, 0, 0, 0, 1. The output is high only if all the inputs are high. I can have a three-input AND gate: A, B, C. Again, the output is high only when all inputs are high. That is the AND gate. So we've got that here. The next one is our OR gate. Our OR gate, that's there, and looks like this. Right there, A, B, X. Is there is that if A or B are high, the output is high. So that's our OR gate. So in the fourth gate I'm going to talk about is the XOR gate. The XOR gate, right there, A, B, X. And I messed up. I forgot 0, 0. Right there. This one is different because the output is high if A or B are high, but not both. Right there. Those are the four basic types of gates. You don't see the XOR as much as the others. Now we've got two other gates that are very, very common, and matter of fact, they're the most common types of gates. That's there. One is the NAND, and basically that's an AND gate with a bubble shown here. So it's the same thing as an AND gate with an inverter on the output. Right there. So if you look at this truth table, if we look at the AND truth table, it's A, B, X. This is the AND right here. Right here. Right there. It's just simply this column inverted right there. Because what this really is it's an AND gate with an inverter right here. Only instead of showing the inverter, we just show it as a little bubble on the output right there. Later on, this gate's going to be a very important gate because we're going to find it's the only gate we need. All the other gates we can make disappear and just use NAND gates. Right there. So, and then the other one is the NOR gate. And again, it's the same as the OR gate, only we put the bubble there. Right there. And again, this is only going to be, this is just simply the inverse of the OR gate. So those are all the basic gates that we use. Right there. Now our next thing is we can now write expressions right there, and I'm going to have a few expression things to point out right there. There. We can write an expression AB. This is the same thing as saying A and B right there. And our circuit for that is going to be like this: A, B, X right there. X is equal to A, B right there. So that's how we represent the AND function right there. Our OR function, A, B, X, is A plus B equals X. Now, these symbols will make more sense when we start doing Boolean, doing algebra on these, right there, using what's called Boolean algebra. Now, our XOR, I haven't done the inverter yet. XOR A, B, X. It's A plus and a circle around here. B equals X right there. Now our NAND, here's our NAND gate. A, B, C, or X. And it's A, B with a not across there. Or not AB right there equals X right there. Same thing with the NOR. Here's our NOR function right there, A, B, X. So we can say A plus B, X equals X, or we can say not A plus B. Right there. And the one I did not show is the inverter, and the inverter is shown often as A and A not like this right here. Or you can say not A right there. This is the more common way that you'll see that there. So these are our Boolean function, or all our logic gates we're going to talk about. That there, and it's pretty much all the logic gates we're going to be using in terms of pure logic gates. These are all the building blocks for the most of the rest of the semester. Later on, we're going to add things like flip-flops and adders and counters and things like that there. And I don't think I'm quite ready to wrap up here. How long have I been talking? Oh, an hour and 2 minutes. We've got at least 15 more minutes there. There. Trust me, I look at my watch too. I sat there just to keep track of it there. So, okay. Let me just start going through, and this is the highlight of what I'm going to cover for new information today, is how we would draw circuits from expressions. That's there. Later on, we're going to look at how we simplify expressions. But I will say, write the expression for AB plus C like that there. That there equals X. Now, how do I get this expression? And then how do I analyze that there? First off, this is an AND gate. We have A going through here. We have B going through an inverter here. That there. And then we have C here, and these go into an OR gate right there. X right there. That's how you would draw that circuit from right there. Now, the next hard part is how do we come up with a truth table for this? And that's kind of a pain in the neck. And this is a long, drawn-out process. This will probably take me close to the end of my class today when I show putting this into a simulator and how that would work. So I'm going to write A, B, C, and then X here. Now, what we can do here is, I'm going to actually, let me, this is supposed to be just, I'm supposed to be able to just zoom this in with 2 fingers, but it doesn't want to work. My zoom is not working that there. Okay. let me move this over here and see if I can do this here. I'm going to put over here, I'm going to put A, B naught right there. And we're going to analyze that first. And then we're going to do A naught B plus C. And the reason I'm going to do this is because it's a little simpler to analyze this one by itself instead of the whole thing. So 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1. And I know it's getting close to the end of the hour when I'm making these foolish mistakes, right? And you should set that there. So when I look at this here, and I'm going to put some lines here to make it a little easier to see what's going on here. Now we're doing an AND function right here. So that means that 1 has to be high and B has to be low. Well, any place that A is low, I can put a 0 here. Right? Get there. In any place B is high, I can put a 0 here. So that's that function right there. That there. And lo and behold, it looks like that there. So now, as I go through, I'm going to look at my final one. I will look at this table and this table right there. That's there. Because I'm going to say A not B, or C, right? So any place C is high, I can write a 1 there. Because remember, the OR function, it's one or the other has to be high. They don't both have to be high. So C is high, I can put a 1 here. C is high, I can put a 1 here. C is high, so I put a 1 there. Then I come back to this table, and I put a 1 wherever that's high. Every place else I put a 0 right there. So this is what my output function is going to look like. It's right there. Now, I'm going to test this using some software you haven't seen before, but I just want to kind of show. And did I put it over here? No, I did not. Okay, let's all apps. Oh, it says it's on start. Okay, well, we'll go ahead and run the software here. I didn't see it there. And this is the way that we will simulate this right there. And right here. And my function was A, B naught, or C, right? So I'm going to go through here, and I'm going to see how that works. I have 3 inputs, A, B, and C. Right there. I have a not that I put on B, right? I have an and 2 that I'm going to put here. Then I have an or 2 that I put here. And then I have an output right here. And I put here. So I'm going to connect everything up. And later on in the lab, you'll get an opportunity to use this software. Okay. So there's our circuit, right? X. So there's our basic circuit right there. And what I'm going to do now is I'm going to go through and simulate this thing real quick. Let's save it. And I'm just going to create a new, up there, digital, and this is 15 September, right there. Right there. Create a new project, and pardon me, I need to, because of the poor resolution of that screen, I can't hit the OK button on the box without unplugging the projector. So I've gone ahead and saved it. So I'm just going to go ahead and compile it, and I'm just going to go through and we're going to put A, B, and C in there, and we're going to see whether it matches that truth table. That's there. Now, if I had the development board, I could download it to the board and actually test it right there. But I'm just going to show how we would verify this with software. Right there. So we've designed our circuit. So let's go ahead and do here. And I have to do a few things here, and again, just ignore what I'm doing because I will explain it to you later. But I just want to kind of go through this here. I want to group these. The reason I group them is it saves me time in drawing the waveforms. Right there. Right there. And you can see here that we go from 0 to 8 right there. A is our least significant bit right there. See, and that should be matching our truth table right there. So the reason I group them is so that I can just tell it to do a count and I don't have to do that there. So once I've got that there, I just go ahead and save this. And I run the simulation right there. And what I see here, and that's kind of an interesting thing there we got going here. I may have made a mistake here. No, that was 50 nanoseconds. Oh. Right there, simulation report. That looks fairly interesting. What is happening here? Oh, we got all kinds of glitches happening here. Okay, ignore these glitches here. Let's kind of right here. This is the table we're looking for. Let's go over here. Right here, and look at our data here. Right here. Oh, wrong one here. Oh, I must have closed the simulation report. Okay, that's hopefully we can see this here. Unfortunately, our screen resolution does not help me any here. Right here, okay. hopefully, as we look at this right here, we can see when it's 0, our output's supposed to be 0. Right here. We can see where it's a 1, it's supposed to be a 1 there, right? We see our 1 here, up there. Now, notice that I talked about these propagation delays. That's showing this delay right here. Up there, you can see that there's a delay between here and here. That causes some interesting things to happen. We go to 2, our output goes low. That there, we see our output go low, again, after a delay. And then it should not go low again until we get back to 0. I mean, it stays low at 2, and then it goes low at high at 3, and it should stay. Now, here's one of those glitches I talked about. We're going to ignore those glitches in this class here. If we were a real engineer working on a real system, that glitch can cause sometimes a major headache. But since we're understanding the basics, we're just seeing our output stay high until we get back to 0. So what we're seeing here essentially here is that our output is low at 0, it's low at 2, and then why is it showing low here at 6? Or no, or is it low at 6? It should be low at 6. Now, that's interesting. Why is it showing low at 6 there? It shows low at 6 on all of them up there. Right there. That's our circuit is right. Maybe my table is wrong. 6 is, you know what? My table is wrong. This should be a 0 here. And the reason it should be a 0 is that B is high, so this should be a 0 here, right there. So I made a mistake in the table. That there. So our simulation works, but my table is wrong. With me finding myself making a careless mistake, it's time to call it a day. Right there. So we'll end with me